Now we talking about some problem of partial differential equation. First problem of a finite string. Let a thin homogeneous string which is perfectly flexible under uniform tension lie in its equilibrium position along the x-axis. The ends of the string are fixed at x equal to 0 and x equal to L. The string is pulled aside a short distance and released. If no external forces are present which correspond to the case of free vibrations, the subsequent motion of the string is described by the solution u of xt of the following problem. Utt minus c square uxx equal to 0, 0 less or equal to x less or equal to L, t greater equal to 0. Utt means the partial derivative with respect to t, and uxx partial derivative with respect to x. So subject to the boundary conditions, u of 0 t equal to u of L t equal to 0 at t greater equal to 0, and the initial conditions u of x 0 equal to f of x, u t of x 0 equal to g of x, and 0 less or equal to x less or equal to L. So let a thin homogeneous string which is perfectly flexible under uniform tension lie in its equilibrium position along the x-axis. String of ends of the string are fixed at x equal to 0 at the point x equal to 0 and at the point x equal to L. The string is pulled aside a short distance and released. If no external forces are present which correspond to the case of vibrations, the subsequent motion of the string is described by the solution u of xt of the following problem. We discussed the about vibrations in previous classes, and now we solve this problem by separable of variables. Let the solution of this problem of the form u of xt equal to capital X of x capital T of t. Then u of t equal to capital X of x capital T of double dash of t, and uxx equal to x double dash of x capital T of t. Substituting the above result in one, we obtain 1 by capital X of x double dash of x equal to 1 by c square capital T of t capital T double dash of t equal to mu c, shaping mu a constant of separation. Therefore, x double dash of x minus mu of x equal to 0, and capital T of double dash of t minus c square mu capital T equal to 0. Case 1. Let mu equal to lambda square which is greater than 0, lambda being real. Then the solutions of 4 and 5 are given by this: capital X of x equal to c1 e to the power lambda x plus c2 e to the power minus lambda x by integration, and capital T of t equal to c3 e to the power c lambda t plus c4 e to the power minus c lambda t is integration with respect to dt. So where c1, c2, c3, c4 are arbitrary constants. In this case, the solution of the equation 1 is u of xt equal to c1 e to the power lambda x plus c2 to the power minus lambda x, and in multiply by c3 e to the power c lambda t plus c4 e to the power minus c lambda t. By the given boundary conditions, we have c1 plus c2 equal to 0 and c1 e to the power lambda plus c2 e to the power minus lambda equal to 0. Now determinant 1 1 e to the power lambda e to the power minus lambda মানে coefficient determinant, coefficient matrix determinant gives e to the power 2 lambda equal to 1. So lambda equal to 0 or mu equal to 0, which contradict that mu is greater than 0. We assume in case 1 mu is strictly greater than 0. So now is this determinant is non-zero. So consequently C1 equal to C2 equal to 0, which is able to give only the trivial solution of the given problem. So we interested in non-trivial solution. Now case 2, let mu equal to 0. Then the solutions of the equations 4 and 5 are given by the integration capital X of x equal to c1 plus c2x and capital T of t c3 plus c4 t. This is clear where c1, c2, c3, c4 are arbitrary constants. So in basic integration, I hope you know. So in this case, the solution of the equation 1 is u of x equal to c1 plus c2x in multiplied by c3 plus c4t. By the given boundary conditions, we have c3 equal to c4 equal to 0. It fails to give the non-trivial solution of the problem. Next, more interesting case. So let mu equal to minus lambda square, which is greater than 0, lambda being real. Then the solutions of 4 and 5 are given by capital X of x equal to c1 cos lambda x plus c2 sin lambda x, and capital T of t equal to c3 cos c lambda t plus c4 sin c lambda t, where c1, c2, c3, c4 are arbitrary constants. in basic level of integration, as you know, in this case the solution of the equation 1 is u of xt equal to c1 cos lambda x plus c2 sin lambda x is multiplied by this. So by the given boundary conditions do we have, where c1 is equal to 0 and sin lambda equal to 0, that or when sin lambda equal to 0, if lambda equal to n pi, so or lambda equal to n pi, while n equal to 1 to 3. So while lambda is equal to n pi by l, where n equal to 1 to 3 and so on, which are called the Eigen Values. So the corresponding solutions are given by un of xt is equal to c2 multiplied by sin n pi x by l and is multiplied by c3 into cos n pi ct by l plus c4 sin n pi ct by l, where n equal to 1 to 3 and is equal to sin pi x by l is multiplied by n cos n pi ct by l plus bn sin n pi ct by l, where n equal to 1 to 3, where n equal to c2 c3 and bn equal to c2 c4, and this is clear. So c2 is multiplied by c3 and c2 is multiplied by c4. So we let n is equal to c2 c3 and bn equal to c2 c4. So this equation is denoted by the number 6. Now by the principle of superposition. What is principle of superposition? Now when two or more of the same type, when two or more waves of the same type cross at some point, the resulting displacement at that point is equal to the sum of the displacements due to each individual wave. So when two or more waves of the same type cross at some point, the resultant displacement at that point is equal to the sum of the displacement due to each individual wave. So now we have e of xt is equal to summation n equal to 1 to infinity sin n pi x by l is multiplied by n cos n pi ct by l plus bn sin n pi ct by l is denoted by the number 7. So now using the initial condition u of x equal to f of x, we obtain summation equal to 1 to infinity n sin n pi x by l equal to f of x. Differentiating both sides of 7 partial with respect to t, we obtain this is clear. Ut of xt is equal to summation equal to 1 to infinity n pi c by l sin n pi x by l is multiplied by minus n sin n pi ct by l plus bn cos n pi ct by l. Now using the initial conditions ut of x is equal to g of x, we obtain so summation equal to 1 to infinity n pi c by l bn sin n pi x by l equal to g of x, and summation n equal to 1 to infinity n dash of sin n pi x by l equal to gx, where n dash is equal to n pi c by l bn. So observe that summation equal to 1 to infinity n sin n pi x by l and summation n equal to infinity n dash of sin n pi x by l are half range Fourier series. These half range Fourier series we will discuss after this semester, and you know about some problem using Fourier series. So n equal to 2 by l integration 0 to l sin n pi x by l equal to f of x, or n dash equal to 2 by l 0 to l sin n pi x by l gx, and hence desired solution is given by u of xt is equal to 1 to infinity sin n pi x by l n cos n pi ct by l plus n dash sin n pi ct by l. Hence the required physically meaningful solution is obtained from equation 7, where n and n dash are given by the equations 8 and 9. Un of xt is given by equation 6 are called normal modes of vibrations, and n pi c by l is equal to omega n, where n equal to 1 to n are called normal frequencies. Now let's talk about another problem of a semi-infinite string with a fixed end. Let us consider the one-dimensional wave equation utt minus c square ux is equal to 0, where 0 less or equal to less than infinity, where t is greater equal to 0. Subject to the boundary conditions u of 0 t equal to 0, where t greater equal to 0, that is x equal to 0 is fixed, and the initial conditions u of x equal to f of x and ut of x equal to g of x, where x is greater equal to 0. Here the boundary conditions u of 0 t equal to 0 follows that ut of 0 comma t is equal to 0 for t greater equal to 0. Observe that f of x minus t, this term you know in the D'Alembert's formula. Observe that f of x minus t does not exist for t is greater than x by c, because for fixed t naught is greater than 0, x minus ct equal to ct naught, which is greater than 0 implies x is greater than ct, which is not possible. Thus D'Alembert's formula cannot be used here. We discussed in the previous class this D'Alembert's formula. I hope you read this term. So let us consider following modified problem for an infinite string utt minus c square ux is equal to 0, where minus infinity less than x less than infinity, where t greater equal to 0, subject to the conditions u of x 0 equal to capital F of x, ut of x 0 equal to capital G of x, where minus infinity less than x less than infinity, where capital F of x this equal to f of x if x is greater equal to 0, and minus f of x if x is less or equal to 0, and capital G of x, which is when x is greater equal to 0, g of x, and minus g of x when x is less or equal to 0. So capital F of x and capital G of x are both odd functions of x satisfying the given boundary conditions. So by the D'Alembert's formula we have, so by previous lesson we discussed this formula, v of x2 equal to 1 by 2 capital F of x minus ct plus capital F of x plus ct plus 1 by 2 c integration over x minus ct to plus ct capital G of r dr. So differentiating partially with respect to 2, you obtain this, and by Leibniz rule. So in this way, by Leibniz rule, and in the calculus, differential calculus, ut of x equal to c by 2 minus f dash of x minus ct plus f dash of x plus ct plus 1 by 2c capital G of x plus ct del t of x plus ct minus g of x minus ct del t of x minus ct. So this formula, so ut of xt is equal to c by 2 minus f dash of x minus ct plus f dash of x plus ct plus half of g of x plus ct plus g of x minus ct. So u of 0 t equal to half of f of minus ct plus f of ct plus 1 by 2 c minus ct to ct is g of r dr, and ut of 0 t is equal to c by 2 minus f dash of minus ct plus f dash of ct plus half of g of ct plus g of minus ct. So this calculation is clearly. So since f and g are both odd functions, so u of 0t is equal to half of minus f of ct plus f of ct is plus 0 equal to 0, and ut of 0t is equal to c by 2 minus f dash of minus ct plus f dash of ct plus half of g of ct minus g of ct is equal to 0. In fact, since f is an odd function, so f dash of minus ct plus f dash of ct equal to 0 implies c f dash of ct minus c f dash of minus ct equal to 0 implies f dash of minus ct equal to f dash of ct. Again, e of x 0 equal to half of a capital F of x plus capital F of x equal to capital F of x equal to f of x for x greater equal to 0. So ut of x 0 is equal to c by 2 to minus f dash of x plus f dash of x plus half of capital G of x plus g of x equal to capital G of x equal to small g of x for x is greater equal to 0. So thus the initial and boundary conditions are satisfied. Observe that g of x equal to 0 if the string is released from the rest. Here the desired solution is given by e of x equal to half of f of x minus ct plus f of x ct for x greater equal to ct, and half of f of x minus ct minus f of ct minus x. This is for x less or equal to ct. So or complete our solution.